Okay, hello everyone. This is EE124 lecture 4, right? Because I'm traveling, so this lecture is for September 4th, Wednesday, but it is pre-recorded on August 28th, 2019. Please watch it, finish it before the next class. We will talk about MOSFET physics and MOSFET models today. MOSFET stands for metal oxide semiconductor field effect transistor. In short, it's just a transistor, right? And it is very important to understand the underlying physics so you know how to analyze the circuits built from MOSFET. Announcement. We have posted assignment 1. Please try to do it early. And also, lab report is due on the week of September 4th, okay? Make sure you know all the grading criteria, okay? There are some mistakes that can give you zero score for the whole report. It's not just that section, okay? So please read them carefully, and the links are all in the Canvas assignment, okay? If you have any question, ask me or TA. Okay? I don't want you to get 0 after working for so hard. Articles of the day. This is pretty interesting. It's talking about global foundries and TSMC. They have some legal allegation at this time. Global foundries is a foundry that was previously formed by Standard Chartered in Singapore and AMD in the US. So it is a spin-off from the Global Foundry, from the AMD, right? So both of them are, TSMC is the foundry in Taiwan, and now Global Foundry trying to get an injunction, right, to stop the customer importing the products they fabricated in TSMC. So basically they try to say that TSMC has used some technology they have patented earlier to produce the chip. Right? And in order to stop that, the best way for them is to stop the customer who use TSMC foundry to produce the chip from importing their product into US and EU. Okay, so why they want to do that? There are many possible reasons, right? But no matter what, this is usually a strategy, right? So that's why all the foundry or semiconductor firm, they try to file as many patents as possible, because this pattern is going to help them in the downtime or when they have any argument with their competitor, right? And this is very interesting. Like you see that here, you also say TSMC also has one of the largest semiconductor portfolio, right, with more than 37,000 patents, right? So with the allegation, liquidation from the Global Foundry, TSMC is going to do similar thing. They are going to sue them backward to protect themselves. Right? So if you want to be successful in this business or actually any other technology business, it is not just about technology. It's about also filing enough and also useful patent for yourself. Okay? But of course, from some people's point of view, they just say this is just a waste of money that mostly goes to the lawyer. This doesn't work. But it will just slow down everything, and actually it can drag the industry growth also, right? And at this time, the whole economy in the world is actually pretty daunting, right? For example, you see the US is escalating the trade war with China. At the same time, Japan and South Korea also have trade war going on. Japan tried to restrict the export of key chemical materials to South Korea. Okay, so let's go back to the main topic. So what did we learn in the last lecture? What did we learn? The most important thing is the op-amp non-ideality, right? Remember that for an ideal op-amp, we have many nice characteristics. But here we actually have something really bad for an op-amp. For example, it has offset voltage. So what is an offset voltage? It means that even, let me put here, this is an op-amp, right? it means that even I put 0 volt into the both the input, I get something larger than 0 or smaller than 0. So I should say this is not equal to 0. Why? Because we can model this effect as if we have a series offset voltage source there. So as a result, even you put 0 to this black box, your output is not 0. Okay? And we remember that this offset voltage is going to have a very big impact on integrator. When the integrator has 0 input, we expect that the output should be 0, right? But if you have offset voltage, even you don't have any input, the output will keep growing up because it's integrating over time, right? So this is very bad. We also say that we might have the input bias current. This will also cause the outputs to be non-zero, even if you have 0 input. Right? But the most important thing we need to remember is the speed limitation. There are 2 types of speed limitation. One is that it has finite bandwidth, right? We always say an op-amp has a gain which is equal to A0, right? But this is the gain for DC when the frequency equal to 0. In reality, if you try to increase the frequency, the gain will reduce. And eventually, when you reach a certain frequency, it will drop very fast. So what is this frequency that it starts dropping pretty fast? Right? What is this? This is the minus 3 dB, right? Or we say this can be the pole of the system, right? So for a long ideal op-amp, how we model the gain, we actually will model it with this function. Okay, so you have a DC gain of A0, which is a real number. Remember, this is a real number, right? Someone asked it in the last lecture. It's a real number, right? And then it's divided by 1 plus S over omega 1. And this is going to model this curve pretty well. And do you remember when it reaches, the gain reaches 1, it reaches 1, right? In log scale, it becomes 0, right? When it reaches 1, we call it, what is this? What kind of bandwidth is this? F1 is negative 3 dB. Fu is unity gain bandwidth, right? It is talking about the frequency at which the gain is 1. And we know that we derive that Fu is just equal to F1 times A0, right? Or you would put in omega, angular frequency, it becomes omega U equals to omega 1 times A0, right? Where omega equal to 2 pi f, right? Which is called the angular frequency, okay? So you see that gain is not ideal when you go to high frequency because the op-amp cannot respond immediately. But there's another more important phenomenon called slew rate, which we did not learn before. I guess we did not learn in the EE124 or other classes yet, right? It's just saying that, okay, if my input voltage is large input, okay, it's not about frequency, it's about the magnitude. When we have a large input, then the output cannot go fast enough. The change, which is the dV out dt, the slope of the output, which is called the slew rate. Okay? It is limited to certain value. If there's no slewing, right? You see, I have this curve 1, then I expect the step response will be this one goes up in this speed, right? Then if I have a higher voltage, I expect it goes up even faster. But it turns out that because the op-amp cannot deliver enough current, as a result, it will go up slowly like this. Although eventually, note that they all reach the same voltage. For example, this is 1 volt, right? This is 2 volt, 2 volt, right? 1 volt. They reach the same voltage, but it takes much longer time to reach the same voltage when you have slew rate issue. Okay? So what is the problem of having the slew rate issue, right? So let's look at this amplifier. Can you tell me again, what type of amplifier is this? Is it long inverting or inverting? Right? So this is a long inverting amplifier. Right? Because the input goes to the plus terminal. And we remember the gain of the long inverting amplifier is 1 plus R1 divided by R2, right? Means V out divided by VE equal to 1 plus R1 divided by R2, right? So what is V in here? V in, we can say that, oh, this is just like V0 times sine omega t. It's just a sine function, correct? So as a result, what is V out? Of course, it is V in times 1 plus R1 divided by R2, right? It's just written here on the left, right? And since V in is V0 sine omega t, so this becomes V0 sine omega t 1 plus R1. Right, so this is the ideal case, meaning that no slew rate, right? Low slew rate issue. If it responds very fast, my output is going to give me this. Okay? But now our goal is that to investigate. Is there any slew rate issue in this case? Let's see, right? In order to investigate, what is a slew rate again? It is dV out dt. It's talking about the rate of change of the output. Of V out, right? So you just do differentiation. V0 is constant, no change, right? 1 plus R1 divided by R2 here, no change. How about sine? It becomes omega cosine omega t, right? And this is what we get here. Now here shows you the dV out dt. What is the maximum value of dV out dt? The maximum value of dV out dt, of course, is when cosine omega t equal to 1. Because cosine omega t can be either, the magnitude changes from 0 to 1, right? The magnitude. The value can go from negative 1 to 1, but magnitude is from 0 to 1. Anyway, the largest value it can have is 1. So the maximum value, the slope is just 1 plus R1 divided by R2 times omega, okay? And basically, this is the slope it has, right? This slope is V0 1 plus R1 divided by R2 times omega. Right? Now the point is, if the op-amp slew rate is smaller than this one, then, okay, sorry, here actually I have a typo. This is the slew rate. This is the slew rate. Okay, this one. The light purple one is the ideal output, right? But then the although here it says the input, but the ideal one should be like this one because it's a sine wave, right? But because of slew rate limitation, right here, this one slew rate of op-amp, right? So yes, we our goal is to have a very steep slope, but the op-amp cannot respond. So you see that your sine wave is distorted when there is a slew rate limit. Think about that. Now pause it and think about that. See if you understand. So you see there's an issue here, right? So what we know that the bandwidth is limited by how fast it can respond. But if you have a large input signal, right, the maximum frequency is going to be limited by slew rate also. Right? So why? Now just let's go back to the this equation, right? Let's say I have this op-amp, and then I have this output. This output I can describe as this one, right? It doesn't reach VDD just because of the transistor we're going to learn later. But anyway, it has a maximum, minimum, and the middle is V max plus V min divided by 2, right? And this is the wave, right? So if you do a differentiation, what is the maximum, what is the rate of change of the output that you need? It is V max minus V min divided by 2 times omega cosine omega t, right? This part comes from what? D sine omega t dt, right? Correct? And then the rest is gone because this is just a constant, right? So d, this part becomes 0. Okay, I'm going to write it. Just this circle part, d, this part dt is 0. So what is the maximum of dv out dt? We just said that it's when cosine omega t equal to 1, right? So the maximum rate of this signal is this one, okay? Now, if the op-amp has slew rate equal to SR, let's say again, what is the meaning of slew rate? It can be something like this. It's say 1 volt per, let me make it easy to see, right? Let's say 10 to the power 4 volts per second. It means that it cannot increase output, that is V out, faster than 10 to the power 4 volts in 1 second. Okay, so in 1 second, it only can increase it by 10 to the power 4, 10,000 volts. It cannot increase faster than this, right? If this is the case, then what is the maximum frequency it can handle? Of course, we need the slew rate to be larger than V max minus V min divided by 2 times omega, right? This is what we prove here. Because for every sine wave, the maximum rate of change is V max minus V in divided by 2 times omega. Right? This is the maximum rate. For example, we can say that it is 10 to 2 times 10 to the power 4 per second, for example, right? And our op-amp only have a slew rate of 10 to the power 4 volt per second. That means we cannot increase the output so fast as what it is required for this sine wave, right? Then there will be a problem, right? So to have it working, we need the slew rate to be larger than this term, right? And because of this, then you see that your maximum frequency you can have is slew rate divided by V max minus V in divided by 2. Right? So you see the slew rate eventually limit the maximum frequency you can have. Now, it's saying it limit it by distorting your signal. Right? Let's go back to here. It makes the shape distorted, so you lose the fidelity. But how about the frequency? It doesn't change. I mean, the met amplification, the peak is still the same, right? So you see that compared to bandwidth, regular bandwidth, right? Let me summarize here. Slew rate, what it does is distortion usually, right? But the gain, A, which is the gain, right, not change. Bandwidth, usually what we say is not about distortion, but the gain reduce. Remember, in the last lecture, I showed you the ABC, the free region of a body part. At higher frequency, the gain reduce, but the shape is still the same, no distortion, right? So this is the major difference between slew rate and bandwidth. Okay? Think about that. Now, another problem for the output resist, the long ideality is that the finite output resistance. Remember, for ideal op-amp, right? For ideal op-amp, what do we have for the output resistance? Is out equals to 0. But in reality, it is not, right? So how do we draw it? It's very easy. For example, this one is the, what kind of amplifier? Non-inverting or inverting? Think about it. So this is a inverting amplifier, right? Because the input goes to the inverting node. So how do we add the output impedance? We just add here, out. Okay. Now, so with this, then you will get the gain instead of the regular negative R1 divided by R2. You will get this. Why it is bad? Yeah, it is bad because it means if you have R out, right? The gain is changed. It's not what we expect. Right? Unless we have infinite gain, then you go back to the previous equation. Okay, here remember here A0 is finite. Right? I just remind you, this is the gain for inverting amplifier with finite A0, right? So in your assignment, I ask you to derive this equation, okay? It's a little bit tedious, but I hope you just to go through the exercise again. Write down the op-amp equation, write down the KCL, KVL, step by step, and you can do this in a few minutes. But be very, very careful in your math. Okay? Think about it. If okay, then let's move forward. You can pause the video if you want. So we're done with the op-amp in a black box, right? So we learned the ideal op-amp. Why do we want to learn ideal op-amp? In engineering problem, we always learn something that is ideal, not because we are lazy. It's because if we know what is ideal, we know the goal of our design or of our task. When we design something, then we will try to design it so that it will be as ideal as possible. For example, the gain as large as possible, the input impedance as large as possible, the output impedance as small as possible, and the bandwidth as large as possible. That's why we learn the black box first, okay? Now we are going to build it. Now it's no longer a black box. We have to build it, right? To build it, we need to know the physical characteristic of all the components. And the major components in any analog integrated circuit nowadays is the MOS transistor, right? If you forgot, MOS refer to metal oxide semiconductor transistor, MOS. Why? Because it has a metal gate, although some of them has poly gates, but this is the gate, metal. And then it has an oxide, which is insulator. And then underneath it is the semiconductor. And what is the most popular semiconductor nowadays? It is the silicon, right? That's why it's called MOS. Okay? And it's called transistor. Why? Why is called transistor? We'll discuss later, right? Here I try to put a slide because in the last two semesters earlier, some students asked, what is the difference between digital, analog, and RF circuit, right? It's good to, now I think it's a time to distinguish them now. Digital circuits, they are actually just circuits. They are the same, no difference. It's just how the human being see it, right? For digital circuit, it's very complicated, but actually we have a lot of full swing. For example, this is inverter. The inverter, you have the input, you have the output. If you have a low input, then you have a high output, right? And then when you have a high input, you have a low output. But we really don't care what happened in between. Our goal is just to map the logic to 0 and 1. We don't talk about 1 volt, 2 volt. We only talk about 1, 0, binary. But of course, as a circuit designer, actually you need to go into the details in order to go through this curve to know how fast it will switch. Actually, it's not as simple as 1 or 0. But this is digital circuit, meaning that when we process the information, we only care about 0 and 1. We don't care about 1.2 volt, 2.2 volt. For analog circuit, it's different. We care about the voltage at different points. However, we actually only care about small signal. We're talking about maybe 10 millivolts of swing, right? Here we are going from, for digital circuit, we're going from 0 volts to maybe, let's say, 5 volts, right? Here we're talking about small signal, right? A very small swing of the signal. That is the signal we want to process. In digital circuit, the signal we try to process is 0 and 1. The signal we try to process is 0 and 1, which correspond to 0 volt and 5 volt, for example, right? In analog circuit, all the signal are represented as small signal. We're only interested maybe 10 millivolt or something like that. So we linearize the circuit. It becomes some linear component. So it also follows the linearity, linear algebra. Okay. Then how about RF? RF, you can say it's just like analog, but it has large signal. We cannot linearize it. It has a lot of distortion and full swing. And unlike the digital circuit, eventually the information only captured as in the 0 and 5 volt. The information in RF is everywhere. Right? That's how I see it. Maybe I'm not complete, but I just want you to see that this is the difference between digital, analog, and RF. And now we are in the analog circuit. So remember, we are looking at small signal. Because it is small, we can linearize the circuit. What does it mean by linearization? We are going to show it later in the MOSFET. Okay? A MOSFET is a very complicated device, a lot of non-linearity, but we are going to linearize a certain region because we only care about small signal, 10 millivolts, for example. And then we can do superposition. Sorry, I keep forgetting this word. Superposition. Which means that we can solve the circuit independently on different voltage source and then add them together. Okay? So what is transistor? I just told you what is MOSFET, right? MOSFET just telling you the structure, metal oxide semiconductor. Transistor, after all, is what? It's just a transfer resistor. Okay? A resistor that can amplify electrical signals as they transfer from input to output terminals. Okay? So what does it mean? It fills the third terminal, the gate. Okay? It can change the resistance between the source and drain. So it's just a resistor, but it is a resistor that we can change its resistance by through another terminal, through some method. And you already know that we do that by applying a gate bias to it. Then I can change the resistance between source and drain. Okay? So in digital circuit, it can be just a switch on the wall, right? You turn it on and off. And in an analog circuit, it is just a voltage control current source or a voltage control resistor. Okay? So what is a transistor? Right? Let's review a little bit more. It has 4 terminals actually. What are they? We just talked about gates, right? Gate is the one trying to control the resistance between source and drain. Here to here is nothing but just a resistor. But this resistance is controlled by the gate. So this is very cool. But very usually we ignore this terminal. This is called the body, or called the bulk, or called the substrate. Okay? We need to bias it, right? And usually we bias it at ground for NMOS, at VDD for PMOS. We'll discuss more later. Right? So this is a 3-dimensional picture. The currents go from source to drain, right? From left to right. And then this is so-called the width of the transistor, how wide it is. This is just like a river, right? The water flow from left to right. And this W is just how wide the river is. If the river is very wide, you can flow a lot of water. Same here, if the transistor is very wide, you can flow a lot of current. But what's the problem of making it wide? The first thing, of course, it occupies more area. Area is real estate. Area is money, right? But this is the way to make it stronger. And then the distance between source and drain, what do we call this? We call it the length of the gate, the channel length, how long it is. If it is very long, you can expect that the resistance will be larger, right? Just like a river or anyway, water pipe, when it is long, is there more resistance? You need to apply higher pressure in order to push the water through the long water pipe, right? So since we're talking about water, right? Isn't that this look like the electron goes from the source to the drain? Right? So it's just like the sink we have in our home. That's why this side is called source. It's the source of the electron. This side is called the drain. It's not the drain to drain away the water. And this is the gate. This is just the knob you go to turn on and turn off your faucet. Right? So then now, something very important. We need to follow the convention. Here, I draw a transistor. What is this? Can you tell me? Sometimes people draw in this way, right? Or sometimes they will add this. This is PMOS or NMOS. So think about it, pause it. And this is PMOS. So PMOS, we will put the we definitely put in VDD, right? And then we have something lower bias. Okay? How about for NMOS? NMOS, we usually will draw this. And here we connect it to lower potential. Let's say ground. Alright? And where does the current flow? Current flow from high potential. This is I. Same for this one, current flow from here, right? But for NMOS, let's start with NMOS. What is the carrier for NMOS? Carrier is electron. So actually the electron is going this way, correct? Because electron is negative charge, so it flows opposite to the current. This current is just a convention, right? We don't have something called current, physical stuff called current in the MOSFET. We actually throwing either electron or a hole. Even hole is not physical stuff, but anyway, let's just say we're throwing the electron. Electron is going from the lower potential to high potential. Makes sense, right? Because it's negative charge, of course it flows to higher potential. So where is the source? Source is the source of electron. Drain is where it drains away the electron. And God, this is gate, right? How for PMOS? What is the carrier in PMOS? It is hole. And it's flowing in the same direction as the current. So where is the source? Of course, higher potential, right? Because it's the source of the hole. Positive charge go from high potential to lower potential. So the lower potential point is the drain for PMOS. This is a very, very important concept. I hope that you at least can memorize that. For PMOS, source is at higher potential. For NMOS, drain is at higher potential. Right? So if I give you a circuit to identify the PMOS and NMOS, what you want to identify first is the potential. Which terminal is at higher potential? It doesn't matter how I draw this. This doesn't matter. This is just a symbol. You want to look at the potential. Because now you look back to this transistor. Source and drain are physically symmetric. No one can distinguish which one is source, which one is drain by this picture without labeling. This can be source also. This can be drain also. How do we determine whether this is source or drain? It depends on potential. Which terminal is biased at higher potential? Okay? Please pause and think about it. Make sure that you understand. And let's look at some transistor nowadays, some more advanced transistor technology. Right? Before that, you see this is 14 nanometer technology. I know some of us might not be very familiar with this nomenclature, right? So you know mm, right? That is millimeter, 10 to the power negative 3. Right? So I should actually even remove this m. It can for any quantity, not just meter, right? This is 1 to the negative 3. How about this one? What do we call this? Micro, right? So 10 to the power negative 6. How about N? Nano, right? Nanotechnology. 10 to the power negative 9, right? So in terms of, for example, for length, you can have mm, micro m, nano m, right? So for example, this is 90 nanometer transistor, means the dimension of the gate is 90 times 10 to the power negative 9 meter. 90 billionth meter. Okay? And there's one more thing called angstrom. Angstrom is for width. 10 angstrom equals to 1 nanometer. Right? This is angstrom is very commonly used in chemistry, right, and particle physics. Right? Just some dimension. So I'll show you one of the state-of-the-art technology, not really state-of-the-art, many years ago, 90 nanometer, but for analog circuits, many people still using it. You see the gate oxide is only 18 angstrom thick. Very thin, right? 18 angstrom means how many nanometer? 10 angstrom is 1 nanometer, so this is 1.8 nanometer. Channel length is 90 nanometer. Okay. And you see the gate is formed by something called polysilicon. It's a type of silicon, but anyway, it is a semiconductor. This is a planar technology. But nowadays, people are talking about FinFET. I don't know if you've heard about that or not. FinFET is like something called 3D transistor. Remember, I just emphasized this is so-called planar technology. Planar, right? It's just on the plane, current flowing from left to right on the surface of the wafer. This is the surface of the chip or wafer, right, on the surface, right, just like on your tabletop. Now here we have a new technology called FinFET. It's 3D. You see that this is the surface of the wafer, okay, or the chip, right? The surface. But now we actually have something called fin. This is silicon. Just like the fin of a fish, the fish fin. And then this is the source, this is the drain, this is the gate. So the current is flowing also horizontally, but you see that it's flowing in a volume. It's like a 3D structure. And then the gate is surrounding the whole volume. Okay, this provides a much better control of the transistor. The reason we do that is because our gate length now is very short, 18 nanometer compared to this 90 nanometer. It's so small that we need to go to FinFET so that it can operate well as a transistor. Right? We won't go into detail, but the goal is so that it still operates as a transistor. The problem for planar technology is that when your gate length is very short, you cannot turn it off anymore. That was the problem. Okay, but there's still some new stuff, not just FinFET, not just the 3D shape, including the gate is metal gate instead of poly gate, polysilicon. Why? Because metal gate can reduce the gate resistance. Okay? Metal is more conductive than semiconductor in general, right? It also has something called high K dielectric. What does it mean? Go back to this planar technology. You see that we have oxide here, right? And this oxide is just silicon dioxide. So this becomes a capacitor. The reason the gate can control the channel is through capacitive coupling. So if I can increase the capacitance, I will have a stronger gate control. So now it's used the so-called high K. For silicon, what is the capacitance? You might forget, but basically it is just epsilon of silicon divided by the thickness, right? And this is like 3.9, proportional to 3.9. But if you want high K, for example, so-called hafnium dioxide, so here I should say silicon dioxide, not silicon, silicon dioxide, right? It's still epsilon of hafnium dioxide divided by the thickness. And this can be 30, almost 10 times larger. So it means this is the capacitance, right? So this has a larger capacitance, so it has a better gate control. So this is mostly for digital, but do we need FinFET for analog? Depends. But maybe we don't need that, right? Depends. But you might need to deal with that because you might need to design analog periphery for digital circuit. Right? Although most of the transistor in this technology are used to fabricate a digital stuff, but you still need a periphery. So that's why you still need to design analog transistor and analog circuit using FinFET. Right? So pay attention to this. Right? This is not in the exam, but it's good to know that nowadays people talking about 3D transistor. In this 3D transistor, we have better gate control. We also have metal gate to reduce the resistance, which is very important for analog, right? Resistance, right? And also you have a new dielectric, let's say hafnium dioxide, have a higher permittivity to give you higher capacitance. Okay, so this is a basic introduction to the transistors. Okay, now we go to the a part that let's further understand how the transistor works. We say that the transistor is just a transfer resistor, right? Remember, it's just a resistor from source to drain. But the resistance is controlled by the gate, right? Now let's try to understand the physics. Here is a NMOS or PMOS. Think about that. Right? So it is a NMOS. Why? Because you have N-type source and N-type drain, and you have a P-type substrate. Okay. Now ask yourself, for NMOS, when it is zero bias at both source, gate, and drain, right? What happened to the substrate? Firstly, do you have any current? Any current? Right? You can pause it and think about that. You don't have current. It is very simple, of course, because the source drain are at zero bias. Okay? But anyway, can you tell me, under the gate, what do I have? You actually have a lot of hole. And how about in the source and drain? You have a lot of electron, right? So what is this? This is just like a P and P. And what is a NP? NP is just a diode, right? And the other side is also a diode. It's a back-to-back diode. Can you conduct any currents through a back-to-back diode? You can never, right? So I equal to 0. It's not conductive. So NMOS, naturally, you will just get a very high resistance. Ideally, infinitely high resistance. Okay? But then, let's say we apply a gate voltage to it, positive voltage. What will happen to positive voltage? This is a capacitor. We have been emphasizing that this is a capacitor, right? Because here is the metal or polysilicon. Right? They are just conductive layer. And then here is the oxide. The oxide can be silicon dioxide or hafnium dioxide, right? So this is just a capacitor. When you apply positive bias to this side, what will happen to the other side? You will start pushing the hole away, correct? Once you push the hole away, do you still have hole at the surface? No, right? But when the hole pushed away, what's left behind? You left behind acceptor. If you still remember the EE128, you left behind acceptor, which is negatively charged. Okay? If you forgot, no problem for these cards. The point is that when you push the hole away, you push the positive charge away, you're left with some negative charge. Okay? So that's okay. But now, what is the resistance between the source and drain? You have N and then no carrier, right? And then N, right? Because this is the depletion region. No carrier, it means. It has charge, but those are fixed charge, cannot move. So I is auto 0. R still infinity, right? Because it just cannot move. This is depleted. No carrier. It's just like I put a metal, oxide metal, right? Insulator in between two ends. Okay? So good, so still no carrier. However, if you keep pushing, eventually it will form the free electron at the top. It will start forming some free electron here. Okay? Then what do you get? You get N, also N, N also N. And then I will be larger than 0. R will be finite, right? Finite. Then you can conduct current. Okay, can you pause and try to understand what I've said? If not, try to replay. The point is that for NMOS, when you have 0 bias, you have NPN, no current. Then you have positive bias, you push away the hole, you got negative fixed charge, not mobile, it's negative fixed charge at the channel, just like N, no carrier N, or just like metal, oxide metal, no current. But there will be a point that your voltage is so high, you actually start inducing some free electron here because it's positive. Remember, you just keep attracting, eventually attract enough electron, then you become N, just a conductive layer. Then you have current. Okay? So, you see that there will be a maximum depletion width, right? So, this is because eventually the electron form, we call it inversion layer, formed, and it will screen the electric field. This one I don't need you to really understand, but if you understand that, it's good. Basically, now this was p-type, right? Now I form a lot of electrons. That's why it's called inversion. I inverted the polarity. Once it forms, it just act like a metal. All the electric field will end at this layer. It cannot continue to form a thicker depletion layer. Okay? So what is the threshold voltage? Threshold voltage is when the VG, when inversion layer just formed. Okay, so we keep increasing. First, we push away the hole, and then we have this depletion layer, still not conducting. But until a point, the VG is so high, I form electron inversion layer. And at that point, we say, okay, this is the threshold voltage. After this voltage, it will be conductive. Okay? And what happened to VG smaller than 0? When smaller than 0, go to other direction, right? So if it's smaller than 0, it's still, here is talking about VG is smaller than 0. Like we can think of this in this way. This is the poly, this is the oxide, right? And this is the N plus. If this is negative, what will happen if this is negative? I will just attract a lot of hole, right? Attract even more hole, right? So still off. Okay? And we call this accumulation. Why is accumulation? Because it was whole before and I accumulates more whole. Right? If I make it very positive, the Vg very positive, eventually I have a lot of electron. I inverted it. That's why it's called inversion. So you see the whole process is you go from accumulation where it's very negative, then you go to depletion, right? Accumulation, then you go to depletion when it is positive, but still no current. Eventually you go to inversion. That is after the threshold voltage. Okay, please pause it and think about it. Now, because of this, then we can make MOSFET as a voltage-dependent resistor, right? Why? Because we already say that if I increase the Vg, I'm going to have more electrons inverter under the channel, correct? Then the resistance is going to change. And then, for example, here I can apply it as an attenuator just through the voltage division law. I know V out equals to R1 divided by R1 plus Rm times V in, right? And we are going to change Rm. This is a function of Vg. So tell me, when Vg is larger, more positive for NMOS, what happened to Rm? Rm will decrease, right? If Rm decrease, V out will increase. Okay, so this is something people use to change the voltage at the base station. So quoting this example just to remind you again, a transistor is a transfer resistor and the resistance is controlled by the gate voltage. Because of this, we can use it for many special purposes. Okay. Now, finally, hopefully you still remember the IDVG curve, right? If not, let's try to draw it. Let's try to draw it. Pause the video and draw it. What is IDVG? When I ask you to do AB, draw AB, right? Something, it means that you want to draw this. ID, which is the drain current on the y-axis, VG, which is the gate voltage on the x-axis. That's meant by IDVG. Okay, let's go back. We just discussed when let's even go to negative. When VG is negative, what is ID? First of all, remember, now it is in accumulation. So what do you have? I have N plus, and also a lot of hole, maybe P plus. So this is a back-to-back diode, right? So do I get any current when I increase VG? No, right? And eventually, I increase the VG, what happened? We just said, we push away the hole, right? Let me go back here. I increase VG, and then the hole push away, and then you have this acceptor positive charge, right? So what do we have? Depletion. Depletion of the hole and electron. We have N plus, and then no carrier, and then N plus, right? And we erase this. So still, we don't have anything. Forever? No, until a point. What happened? Until a point, it will pick up. Why? Because at this point, we call it threshold voltage. After this point, we have inversion. What do we mean? N plus, N plus. Now the currents can go up because now you inverted a lot of electron here. So this is a continued channel from N plus N to N plus, right? So that is the IDVG curve. drain current as a function of gate voltage. Pause it and think about it. So how are the device dimension going to change our IDVG, right? So you see that if I reduce the gate oxide thickness, I increase the current. Do you remember why? This is because the gate capacitance equals to epsilon divided by TOX, right? This is the thickness. Again, this is just a capacitor because again, the transistor is a transfer resistor. It's just a resistor, but the resistance is controlled by the gate voltage. And how does the gate control it? It's control it through capacitive coupling. Here is, let me draw here, just a resistor. Okay, to avoid confusion, I think it's better to draw in the middle. Just a capacitor. So if I reduce Cox, reduce Tox, capacitance increase. So I have a more effect. Okay. How about for the gate length? This is the gate length. If it's longer, do you expect larger or smaller current? Just a resistor. Longer resistor has larger resistance, right? Just a resistor. Same for the MOSFET. So if you increase the gate length, your current is smaller. Finally, how about the width? We already discussed earlier, right? Width is just like the width of the river. If I have longer width, then it will be good. Okay? So this is the last slide, I think. But finally, I want to introduce this concept is how people do the layout. This is you are going to do a lot if you're going to be an analog designer. So for a transistor layout, you usually would draw a box like this, right? And then you have another box. And this is looking from top. This is called bird view, right? This is the source, this is the drain, this is the gate. So this is the width, and this is the channel length. But usually you need to probe it, like you need to contact it. There will be a contact here. Okay? And then, so what I'm showing here, this region is this region. Okay? If the width is very long, right? If W is very large, then there is a large resistance from, let me just call this A to B. What do I mean? This is A, this is B. I need to supply the voltage from the contact to the gate. If this is very long, right, it's going to take a long time to reach there. So I have a large resistance. So people will use the so-called multi-finger one. So what do? They will do it in this way. This is the slab. Right, let me draw it first. And then they have something like this. Let me draw it and then explain to you. This is called multi-finger. It's not your finger, right? And this is A. This is the gate. This is the contact, right? So what do? Then this becomes source. This is drain, source, drain, source. The current is going to flow in this way. You see? If this is W, the effective width is equal to 4W because I have 4 transistors running at the same time, right? Then instead of drawing something that is very long, like here, if I make it 4W, there will be a lot of delay. By using this finger structure, the delay from A to B, A to B, A to B, A to B will be only 1/4 of the one that if I only draw them in one finger. So that's why we have this multi-finger layout. Okay? Think about it. If not clear, ask me. Let's talk in the next lecture or the office hour. So I think that's it.